Question 8, so another fixed essay question, but this is on relative rate of hydrolysis. So what we have is acyl chloride. Acyl chloride is RCOCl, and this is versus alkyl chlorides. Alkyl chloride is just halogenoalkane, and the next one is aryl chloride. Aryl chloride is basically halogenoarine, so it's a halogen bonded to a benzene ring, such as like this, and you have I don't know, chlorine or bromine or whatever. Okay, and then halogenoalkane is just RCl. So in terms of these three, which one get hydrolyzed the fastest? Well, this thing is going to be hydrolyzed the fastest due to the two highly electron withdrawing groups there. Between this and benzene ring doesn't want to get hydrolyzed that much, as you know. Despite the halogen being electronegative, if you look in the data booklet, the halogens are actually 246 directing. 246 directing for electrophilic substitution inside the benzene ring. That's because they actually donate the lone pair into the benzene ring despite it being electronegative. Because of the lone pair delocalization, they activate the same as the electron donating groups, meaning to say that this bond is actually much stronger than the single bond that you perceive it to be by looking at this diagram. Therefore, halogenoarine does not get hydrolyzed at all. So from the fastest to the slowest, in fact, that is the exact trend already. From the fastest to the slowest hydrolysis. Okay, so I should go a little bit, move it up there. Is that good enough? Probably not. 246 directing, probably don't want that. Electrophilic substitution mechanism. Anyway, so the slowest to hydrolyze is going to be halogenoarine, followed by halogenoalkane, followed by acyl chloride, which is very fast to be hydrolyzed. In terms of your reason, so well, first of all, halogenoarine first. As I mentioned, the lone pairs on the halogen bonded to benzene actually delocalizes into the benzene ring. Delocalizes into the ring. Therefore, the carbon arine, I should say the carbon bond arine with the halogen is much stronger than expected or perceived than normal carbon alkyl halogen. Okay, much more difficult to break. Okay, so alkyl halides or halogenoalkane has polar CX delta minus, delta plus. Same thing with acyl chloride. But what is different about acyl chloride is that acyl chloride also has a highly electron withdrawing carbonyl delta minus oxygen there. Acyl chloride also has highly electron withdrawing electronegative, very electronegative oxygen. Therefore, making that central carbon very delta positive, therefore susceptible. Susceptible means very prone to nucleophilic attack. Nucleophilic attack meaning like water, and therefore it is very easily hydrolyzed. Okay, so the whole idea is very easily hydrolyzed because of two highly electron withdrawing groups, this one being a more electronegative element than chlorine, therefore making this carbon very delta plus, very susceptible. Nucleophile wants to attack electron deficient, electron poor carbon, just like that. Okay, so that's it for that 3-mark essay, which you can definitely prepare for. Question 8, part B. So you have this particular drug. Ooh, okay. I'm not gonna draw the whole. Should I draw the whole thing? No, I'm not gonna draw the whole thing. Hope you can see the ester linkage. That is your ester. And then you have another ester on the far right hand side, and you have an amide. Amide is going to be this C or NH. All of these are from your O-level or IGCSE chemistry as part of polymerization. And you also learn this in AS for ester and amide in A2 for amino acids and proteins and stuff. Completely hydrolyzed under acidic conditions. So be careful, we're talking about acid hydrolysis. For ester, it's no problem, but for amide, we're going to get an amine and a carboxylic acid. The amines are basic. Amines are basic, which means in acidic conditions, you're going to protonate. So altogether, you get 3 products. So if I just draw out the first product, there's your OH there, and then there is your carboxylic acid there. So I'm trying to follow what I have there so that I don't have to, redraw the very, very big structure. There's your nitrogen there. That is your another ester. So this will give you carboxylic acid, and that will give you your 1 carbon alcohol again. So that is your 1 carbon alcohol there. There's your 1 carbon alcohol there. So these and these are exactly the same product. CH3OH is methanol. They say draw the structures in the boxes. They don't say skeletal, structural, or display. I can challenge you to draw display and see whether you have enough time in the exam or not, which is why you must practice skeletal. Even when you started from AS, skeletal is the way to go. Okay, if you want to excel, if you want to do well for organic chemistry. Onto the next bit, the bottom bit, I have, is that correct? No, on this nitrogen there, I still have my benzene ring. Okay, and then I have my amide there. The amide will break. What happened then is I'll get an NH like that, and then I'll get a carboxylic acid, and this is a 3 carbon carboxylic acid. 1, 2, and 3. This is from the amide. Now they get hydrolyzed. If I draw a pink boundary there. And did I say just now acid hydrolysis? You are getting an amine with a lone pair on the nitrogen. So what happened is there will be NH. Well, the nitrogen will have 1, 2, 3, and 4 because it uses the lone pair to form dative covalent bond to a H plus with no electrons. There's your AS dative covalent bond. So draw the structures for these organic compounds. I have drawn them. So there is just going to be CH3OH, and there is just going to be the propanoic acid, and I can just copy down the big organic molecule, and yeah, that's just it. Okay, so 1, 2, and 3. Do I want that? Yep, that should be all right. So just showing that that is your product 1, there's your product 2, there's your product 3. I guess what's tricky is under acidic hydrolysis, your amines will get protonated. And don't forget that this is also amine. Okay, I just want to highlight the fact that this is also amine, so this could also get protonated. I should have seen it earlier. There is a lone pair there as well, so that should get protonated as well. And when you get protonated, it's a plus. Carboxylic acid doesn't get protonated since they are acidic already, but these are amines with lone pairs on the nitrogens. They can get protonated. For that 3 marks, I don't know how much they'll penalize you if you forget that, but that is very typical in this kind of acid-base hydrolysis type of question. On to the next part. So this is question 8C. This is Proton NMR. So we're looking at compound Y, C5H10O2. It can react with Na2CO3, and you get bubbles, you get effervescence, you get a gas. Anything that react with carbonate and get a gas, that gas is CO2. Therefore, Y has acidic group. Y has acidic group, something which is acidic. In fact, it has to be a carboxylic acid, because even though phenol is acidic, but then phenol cannot react with carbonate, only carboxylic acid. is acidic enough to react with carbonate, with the organic compound. And then the proton NMR in D2O. So what is shown is in D2O. So we know the OH of carboxylic acid, fast exchange. This is a concept for proton NMR, fast exchange with D2O. So you will disappears. This disappears. So essentially what is shown is 3 signal, but then one of the OH disappears, so you're looking for 4 signal in reality for the carboxylic acid. But don't go looking for the carboxylic acid, because what is shown is just from 0 to around give or take around 2.6 ppm. So the OH of carboxylic acid is much higher, which is why they say in D2O, it doesn't matter. This peak wouldn't be seen because you are in D2O. Okay, because you are in D2O, this peak wouldn't be seen at all. So out of the 3 peaks, you have 5 carbons. You have 5 carbons, and it has carboxylic acid. Looking at that, what do we see? We need to suggest a structure for it, and let's see. So if we suggest a structure for it, it's a carboxylic acid. How about if it is a straight chain? So if it is 1, 2, 3, 4, 5, so there's C5H, 3 hydrogen, 4, 5, 6, 7, 8, 9, 10, C5H10, O2. You gotta think about all the possible isomers of it, but then this cannot be because it's got 1, 2, oops, sorry, I'm not looking for carbon, I'm looking for hydrogen. 1, 2, 3, and 4 different hydrogens. Why did I not count this? Because this one was already discounted from the fast exchange in D2O due to labile proton as stated in your syllabus. OH and NH is labile. Fast exchange, you don't count these because you're looking from 0 to 2.6 ppm anyway. 4 environments, you only have 3 environments, so you're not looking for these, so this one can't be the isomer. I can be a little bit cleverer because I see there's a doublet and a doublet. What does a doublet actually mean? A doublet means I have 1 neighboring protons. I have 1 neighboring protons. Let's see. If like that, 1, 2, 3, 4, 5, and that doesn't work, does it? So 1 neighboring protons, this one will see many lines, this will see 1 neighboring proton, so this one 4 and 5 will see a doublet. 2 will see 1 neighboring proton, so 2 will see a doublet. There are 4 and 5 will be the one which is just below 1 ppm because there are 2 environments that overlap as 1. So this is the blue one, and then I can show the red one, which is 1 carbon, and I can show a black one, which is I mean hydrogen. So there is 3 hydrogen there. There is 3 hydrogen for the blue one. So for the blue one, there's 6 hydrogen altogether. And this is going to be CH3 twice CH, and you have 1 neighboring protons, and you have 1 neighboring protons means let's see, 1, you are here, you have 1 neighboring protons, you will get a doublet. Whereas the black one is just got 2 hydrogens, and it's a CH2 next to a CO2H, and when you are here, you don't have any proton there, but you have 1 proton on the other side, so you also have 1 neighboring proton, and you will also be a doublet, but your intensity is lower because you only have 2 protons, so this is going to be the one which is 2.2 ppm, so that has to be the one which is 2.2 ppm. So this is 2.2 ppm. The 6 hydrogen is the one which is around 0.8 ppm. And last but not least, when you are the red color one, not the pink, the red color one, you just have 1 proton, and that has to be the multiplet, which is around 1.9 ppm. You read the middle bit, give or take. So there's your CH3 twice CH2. You are what I have underlined here. You have got many neighboring protons. In fact, you have got too many to count. You got 6 and then 7 and 8. That's why you got many lines. You got many neighboring protons. You got multiplet. You got so many lines. And that's the one you saw at 1.9 ppm. So all in all, use the information to suggest a structure of Y. Y is this, well, what I've drawn on the left. I'm just drawing a little bit neater. If you want, you can draw the structural formula. So CH3 twice, and then you have CH. There's a carbon with 4 bonds, 1, 2, 3. So there must be 1 hydrogen there. And then CH2, and then CO2H. Use that thing to work out, well, I've already worked it out, 0.8. The next one is 1.9. So what I can do is I can just move that down there. Beauty of working on the screen is I get to move things around just as easy as that. Yeah, just like that. Okay. Not very satisfied there because that line doesn't look like it is straight. Don't want to be a super perfectionist, but neither do I want to be super sloppy. That looks slightly better. Anyway, doesn't matter. So the environment of the proton is going to be this one. So this is where you are. Environment of the proton. You can obviously copy paste from the data booklet based on the description that I give you. The splitting pattern there is going to be the doublet or the multiplet or the doublet. Splitting pattern. Number of hydrogen atoms responsible for the peak. This is the integrated ratio, number of hydrogen atoms responsible for the peaks. So I've not done them in exact order, but I hope that makes sense in terms of what we have counted based on these particular things that we have discussed. So that's the end of these 10 mark questions. That runs up one of the most difficult concepts, which is on proton and carbon NMR. But here in this question, it's just proton NMR, part of analytical chemistry. But a lot of it just comes down to whether you can interpret and analyze all the information given. That's the end of that 10 mark question. And this is the end of this June 21 paper 4.2. So it's a A-level paper 4, pretty long by now. I better finish it as soon as I can now. Don't forget to click the button on the bottom right to subscribe to the channel. And please share the channel widely with all your friends, chat group, juniors, seniors, relative, etc. etc. You can follow me at ptet.chemistry on Facebook, Instagram, and Twitter. Send in messages, send in questions. Look forward to hearing from you, and good luck in the exams. Thank you for watching, and see you in the next tutorial video.